Okay, so today we're going to be starting our calculus. We're going to look at section 2.1. Part 1 is our video today. We're going to be looking at this thing called rates of change and limits. Okay, so we're going to start off with an average rate of change. So what is an average rate of change? Well, it is basically the distance traveled divided by the time that you need to travel that distance. This is what you do when you're in a car and you're traveling to grandma's house or wherever you're going. If it's 300 miles away or you're going to the coast, it's 300 miles away. You can get there in, 6 hours. Then your average speed is 50 miles an hour. So how does this look mathematically? What's going on here? So let's take a function y. Let it be a positive function. That means it's above the x-axis. It's a function of a moving object at time t. Okay, so here's our function f is this curve, and here's t, and so we have a point on the curve at t and then f of t. And then a little bit longer in the future of time, so we add a little increment of time here, so this is t plus h. So if this was hour 1, this could be hour 2 or hour 1 and 15 minutes or whatever the case may be. If I want the average, then I have a dot here, and the average is literally what's called the secant slope. So if I draw a line between those two dots, that is a secant line. If you didn't know, a secant line is a line that goes through 2 points. A tangent line is a line that touches only at 1 point. And so the average rate of change is literally the slope of the secant line through the endpoints of your time interval. That's how your average is determined. Okay, and so right here just lays it all out in different forms that you might see in the future here. So the average rate of change, when you see those words, it is the change in the y values divided by the change in the time, otherwise known as the change in the position of your object divided by, so that's the distance traveled, divided by the change in the time. And then they'll do it in a function notation format in this way, 2 different ways. So this is it's called the difference quotient. Okay, it's basically your slope form. Here's y2 minus y1, x2 minus x1. It's the same form that you did in Algebra 1, just looks a little different based off of the time intervals that we have over here. And then if you clean up the bottom part down here, you'll see that the t's will drop out and it's just h on the bottom. So this is your, and h is the elapsed time. And so this is our difference quotient, and we're going to see this quite a lot. So you want to make sure you understand the difference quotients and things like that. So let's look at an example I have for us and see how we can use this to our advantage, or do a problem associated with this one. So we're going to do this example right here. So an object is dropped from the top of a tall building and it falls according to this function right here. It'll be in feet and in the first t seconds. So t time is in seconds. Find the average speed during the first 3 seconds. So when we do this, we want to kind of understand what we're talking about and understand the players that are involved. Remember, an average is the distance traveled in a time interval. So we want to make sure we understand what's going on there. And so their time interval is in the first 3 seconds, which means we're looking at the time interval as starting at 0 and going to 3. So this is our interval of time. This would be t, and this would be t plus h, kind of a thing. And so we need to find the top part. So we have f of t plus h minus f of t divided by h. H is the difference of these two things. So h is 3 minus 0, or 3. We need to find these two things up here, okay? F of 0 and f of 3. We need to find those, okay? There's our function for f. And so we have 16 times 0 squared and 16 times 3 squared, okay? And then we can take that information, we can plug it into our little equation over here. So our average rate of change is going to be our change in the y divided by our change in time. And our change in y is going to be f of 3 minus f of 0. And then down here will be 3 minus 0. And then this gives me, oh, I didn't give this answer over here. This is going to be 9 times 16, which is 144. Sorry about that. And so it's going to be 144 minus 0 over 3. And then we clean this up over here and get an answer of 48. And then our units, feet per second. And so that would be our average rate of change. Okay? And so when we would write our answer, we need to say that, because the way we write our answers is very important. This is not really enough. We want to write in context of our problem. And so you would simply use the problem's description in the answer that you found. So the object falls an average of 48 feet per second over the first 3 seconds. And so that is the best way to write your answer moving forward when we do our problems in here. Okay? So let's look on the next thing. Okay, let's look at our next view here. And we ask these questions. So there's the problem again for those who want to pause and copy that question down. So the next question, though, is this. How do we find how fast an object is falling at 3 seconds? This average is over 3 seconds, but I want to know what happens at 3 seconds. How fast is it falling at that instant? And so we get the instantaneous rate of change, or your actual speed at that moment. To answer this directly, we will need to take more tools in our toolbox, but we don't have that for now. We're just going to explore this concept by finding the average rate of change for a smaller and smaller elapsed time, and kind of see if we can get an answer closer and closer and closer to it. Okay, so let's go ahead and do that. We're going to use the information we had up here in our problem to help us find the instantaneous rate of change when t is 3. And so to do that, okay, in the first one, so let's go ahead and look at what we're going to start with. Remember, in our first problems over here, this is basically how the secant slope is determined from this right here. So we're going to use that concept right there to help us figure this out. And I'm going to pick smaller and smaller values for h. Remember, h is how far it is from the initial start. Okay? And our start value is going to be 3. Because we're starting, we want to find out what happens at 3. Okay? And so we're going to use that information there. We can use the other form of it. So we have basically f of t plus h minus f of t. And then this will be t plus h minus t. So our t is going to be 3. And we're going to determine what is h. We're going to pick the h we want now. Okay? So if this is 3, how far am I going to move off of 3? Remember, I want to know what happens at 3. So I'm going to pick an h that's fairly small. I don't need to pick a large one. I don't care what happens at 4. I want to get really close to 3. So let's start off by just picking h to be 1/10. Okay? So that means this will be 3.1, and this will be 3 right here. So let's go ahead and find, at this value right here, what is our average going to be? Our average, which is the change in the y values divided by the change in the t, is going to be f of 3.1 minus f of 3 over 3.1 minus 3. So as we work this out and we plug our numbers in to our equation, remember it's 16 t squared. This is going to be 16 times 3.1 squared. This is 16 times 3 squared. And down here, if I subtract these two values, I'm going to get 0.1. And then we can use our calculator and we can type this in. I'm going to save the time of typing this into our calculator because I've already done so. And you're going to get a number that's about 97.6. Okay? But what I'm showing you is how you need to display your work. So the next one is, well, let's make h smaller. Let's get closer to 3 instead of at 1/10. Let's make h 0.01. So now we're at 100. If I have this value of h, then this problem becomes, so our average is the change in the y, the change in the t is now going to be f of 3.01, f of 3.01 minus 3. Plug those numbers in, and we work this out, excuse me, 3 squared, and this time, these difference down here is going to be 0.01, because that's what h is. And if I type this into the calculator, this answer now becomes 96.16 approximately. So you can see that we're getting closer to a number. We don't know yet. Let's try the next one. Obviously, the next iteration in this one would be, let's let h be 0.001, and let's see what happens. So our average is the change in the y over the change in t. And I can do this, 0.001, f of 3.001, and same thing as before. And we type this into our calculator when we're done. And you should pause and try this on your own to make sure you can use your calculator properly. You can also use Desmos if you don't have a graphing calculator yet. Okay. And we type this into our calculator, and you notice we're going to get 96.016. And so what's happening here is from here is a bigger change, but from here to here, the 96 is now static, and this 0.616 thing here kind of is going to get a 0 here. So if I went one more time, I'm pretty sure I'm just going to be putting more zeros in here. So the closer I get to 3, it looks like this answer is converging or getting closer and closer to 96. And so that is what it looks like it's going to be, and that would be kind of our instantaneous rate of change. It looks like we're not sure yet. Okay, remember, this was just we don't have everything we need to help us do this problem properly, but we can keep on going, and it looks like it's going to be approaching 96. And which means the instantaneous rate of change at 3 looks like it's going to be 96 feet per second. And so that's how I can use the average rate of change to help me approximate an instantaneous rate of change, because we're just moving this dot right here closer and closer and closer and closer and even closer to the point of interest that we have. And so that's how we can use that to help us find the instantaneous rate of change of a value. Okay? That's where we're going with that. Let's go ahead and take a look at the next part of this, which is what I was just talking about just now anyway. So here it is again. So what happens, and I'll just go ahead and leave this up here so you can see it. So what happens if h is, in the problem, is representing a smaller elapsed time as we get going? So a smaller and smaller and smaller and smaller. So what I've done here is I've done a generalization here. Instead of having the value for h, I just plugged h in here and did the exact same problem again with h involved. So you can see with this value here is 3 plus h. I can plug it into that equation for p, and I got 3 plus h squared. Here it is over here, the same value here, and h is on the bottom. If I expand this out and then times it by 16, this right here is 144. We knew that from a previous problem. Here's h is on the bottom. And I distribute this and combine like terms. This expression becomes this expression. And you'll notice that these two h's right here, after you factor out a common h on top, are going to reduce out, leaving this expression here. Now the thing here is this: What is h? H is the change in time. And I want that to become smaller and smaller and smaller and smaller. So when h approaches 0, well, then the instantaneous speed at time 3 literally becomes 96, because this term right here becomes 0. So what we have shown here is that, yes, if I can make h smaller and smaller and smaller, it is now definitely going to become 96 feet per second. Okay? And I want you to note over here, you can think of an average rate of change as an approximation of an instantaneous rate of change. And so that's what they do in calculus, is they'll use the average. If it's too much trouble to find the instantaneous, I can use an average to approximate the instantaneous. Or I can go through the process here of finding an instantaneous for a specific time. So that's an important concept, what we did right here. You want to make sure you have any questions about this that you ask. You're going to be doing this quite often. Let's go ahead and look at the next topic here. This concept of finding a value of a function as the independent variable, t, approaches a specific value is called the limit of a function. Okay, that's what it's called. This thing that we did up here is finding the limit. What is it approaching? What is the y value approaching the limit that it can possibly get to? Here's the definition of a limit. Let's go ahead and take a look at this thing, or a definition. It's given a function f. The limit of f of x as x approaches some value c is a real number r if the function can be made arbitrarily close to r by taking x sufficiently close to c, but not equal to c. Well, that was a lot of words. But what are they really saying? What they're basically saying here is this. C is some number, some x value, okay, in some interval that we're looking at. If I am approaching c on the x-axis, so if the x value is getting closer to c, what is the appropriate y value getting closer to? So as x moves over here, see there's a y value associated with this x right here. Well, it's right there. But as I get closer to c, my y value is getting closer to what number? It's getting closer to the r. That means r is, since it's a real number, that r is called the limit. So the limit as x approaches c, and it goes from both directions. So x going closer to c here, the y values are getting closer to r over here. The limit as x approaches c, okay, means the y values are going to approach r. As x approaches c, the y values get closer to r. So the limit as x approaches c of the function is r. The other format that you use this for, okay, we did this before, but we did not use the limit definition so much. Maybe we did, I can't remember. But when we talked about in behavior or vertical asymptotes and stuff in algebra 2, you could have done it as x approaches some value, let's say some a value, and then a lot of times we had infinity with us. We had some y approach some like infinity or approach something. This right here notation is an alternate form of a limit. We do not use this format in calculus. We can discuss it, and actually we can use it. We kind of use it up here, but formally it's called a limit, and so you're going to see it as this more often. So if you have any questions about what this really meant, make sure you ask when you come to class, okay? Because this is huge. This is a huge concept for calculus. There's three things you got to know how to do. One is called a limit, the other one's called a derivative, and the other one's called an integration. Those are your three skills, and this is one of them. So you want to make sure you understand what's going on here. As the x values approach some predetermined value on the x-axis, the y values of the function are approaching some number. If that happens, then the limit exists. Okay? And we're going to go into more detail of limits here because that's what we're talking about. And so let's go ahead and take a look at it. All right. zoom in just a tad and maybe give it a little bit more focus here. All right, so sometimes the values of a function f approach different values as x approaches a number c from opposite sides. Okay? This means that we can look at limits from both directions, as I already talked about. A limit from this side would be called the left, and the limit from this side would be called from the right. And to distinguish the two, you'll notice that the notation has a little minus sign up above here, kind of like where an exponent would go. So C and a little minus sign means this is from the left, and a plus sign right there means you're coming from the right. From the negative side, from the positive side. To say that a function has a limit as x approaches c, they're referring to this now, no plus or minus signs, then the left and the right side limits must agree. So, since I can look at things from two directions, when you talk about a limit, you need to do so. You look at it from coming from the left, you look at it coming from the right. If those two limits agree and they are approaching the same y value, then we say that the limit does indeed exist, and this is what it refers to right here. So to say a function has a limit as x approaches c, then the left and right side limits must agree. The limit from the left has to equal the limit from the right, and it has to be a real number. If that happens, then the limit is r, okay? The same value. If I tell you this is true, this is what if and only if means. If I tell you this is true, then that's true. If I say that's true, then you know that is true. So it goes both directions in this situation. You're going to use this concept quite often also, so this is why these are important. Make sure you do include all these things in your notes, please. Here is an example we're going to talk about. This is some things that you're going to be asked to do on an AP exam. So here we go. Weird looking function over here. A lot of stuff going on. Some things you may remember, some things you don't. So we know what this here is an in behavior asymptote, kind of like a slant asymptote. This is a vertical asymptote right here, this dotted line. This is a vertical, although I didn't draw it all the way up, it is a vertical asymptote for this piece down here. These circles mean that the endpoint is not included. That dot means the endpoint is included. We have a horizontal asymptote right here as it continues out. And there's a lot of problems you're going to be asked of this type. There's so many limits I can ask you to look for here. Here is just one example, and we'll do other ones in class together because this is indeed an AP style question. So the limit as x approaches 6 from the left of this function. Does it have one? Well, if it approaches a number, if the y values get closer to a number, then it does exist. Okay? It doesn't have to get closer to a point on the graph. It just has the y values have to get closer to a number. And it doesn't have to be on the graph itself. So let's take a look at 6. So here is 6. Our interest is right here. So when I look at this graph, I see, okay, here's my graph. I have a circle, and then the dot is not in the same spot. Okay? Well, that's fine. It doesn't matter to our problem here for when we're talking about, because limits are about what happens when I get close to something, not what happens when I'm at 6. So I'm not going to 6 until down here. What I'm doing is I'm getting closer to 6. So as I approach 6 from the left, that means I'm over here on the negative side. Look at the y values. What are the y values getting closer to? As I get closer to 6, as I come down here, these y values are getting closer to the number 3. The y value is getting closer to 3 as I get closer to 6. If I got closer and closer to 6, I would be getting closer and closer to 3. I'm not going to step on 6. I'm just going to get closer to 6. So this has a limit of 3. Now let's go from the positive side. So now I'm over here. I'm bigger than 6, but I'm getting closer. So I'm looking at numbers like, in our example, h becomes 0.1, then 0.01, and 0.001, and then 0.000000001. As I get closer to 6 over here, The y values are increasing and getting closer to, again, the same value, 3. It's never going to be 3, but that's not what a limit says. What it's asking is, what happens as I get closer to 6? The y values are getting closer to 3. That's what a limit means. Not what happens at 6, but as I get closer to 6. And I mean really close. Well, our last little rule said this: if the left side limit and the right side limit both agree on a value, then this limit, as x approaches the number 6, this is the big limit. These are mini limits kind of thinking, okay? These are not the same power as this one. This is the big one. But since these both agree, then I know that the limit as x approaches 6 of the function is 3. That's what that meant. But notice what happens at 6. What is the value of the function at 6? Well, it's not 3, is it? It's 4. So what this is illustrating here is for you to understand that the limit has nothing to do with the value of the function that you're approaching, okay? It has to do with as I get closer to that. As I get closer to 6, the limit, the y values are getting closer to 3. But at 6, the value is 4. So you have to separate yourself from the actual value and never forget that the limit is as I get closer. So you're getting closer and closer, not what happens at the value you're talking about. So that's this example. We'll explore this in more detail. So how do I determine the limits algebraically? Okay. What are the properties of limits that I can use? And here they are. I just listed them for you. They're also in your textbook if you need to go look there. These are the properties that I get to use that might help me algebraically determine a limit. Because if I can't see the graph, or I don't have the ability to see the graph because it's not on the calculator portion of the test, then I have to be able to find the limit somehow. And so as you go through these things, I'll go through a couple of them, or maybe real quickly here. The limit as I approach a constant, in other words, a horizontal line. So try and visualize a horizontal line. And as I approach some c value, well, I'm going to get the same value because all the y's are the same y value. It's a horizontal line. So what if I have the function x? Well, think about what the graph looks like. What does an x, y equals x look like? It's that diagonal line, right? It's the diagonal line through the origin. And so in other words, y equals x. So as x approaches the number c, then the y values will approach the value c. So that kind of thing. And so just take a look at this and you can kind of see some techniques that we're going to be using here as we talk about it. But if I have a constant times a function, well, then I can actually find the limit of the function and then just times it by that constant. This is another technique we'll be using. What if I have more than one term? This would be an example of like saying, okay, hey, what if I have x squared plus 3x? I can think of this as a function and think of this as another function that I'm adding together. So if I want to find what is the limit as x approaches 1 of this function here, I can look at it as the separating of it. I can find the limit as x approaches 1 of x squared, and then add to it the limit as x approaches 1 of 3x. That's what this one here is saying. And then the answer will be just be their sum. Okay? And so that's what this is referring to right here. Here's a product of two functions. That means if I had x squared times 3x, again, I can separate it out and do the limit of this piece, and then the limit of this piece, and then multiply those two limit values together. That's what they're saying there. What about division? Well, same thing. You just divide the limits of each individual piece, provided the limit on the the function on the bottom is not 0. Remember, you can't have 0 on the bottom of the fraction. And then here we have exponent stuff. So I can take this right here and find the limit of f of x, and then just raise it to the same power. So these properties assist us to find things algebraically. But you need to remember a couple things, and here's what they have here. Let me move some stuff so you can see it. An important note, be careful. So if the limit as x approaches c of a function f of x and or this one right here does not exist, and we abbreviate it with D and E. If it does not exist, that does not automatically mean that a limit, I can't read my own writing, involving, sorry. So that doesn't mean that the limit involving both functions does not exist. It just means that you cannot use these properties up here to evaluate it. Okay? So let's take a look at that. Here's an example that illustrates it. Here, as x approaches 0 of this function, it does not exist. See? The limit from as x approaches 0, on the left, it's this number 1. On the right, it is -1. So they do not agree. So this limit does not exist at 0. It'll exist other places, but not at 0. Well, here's G. It's just the exact, opposite of those. So over here it's -1. From this direction it's +1. So this one does not exist at 0 either. But if I add these two functions together, they become this graph right here. And this graph, as x approaches 0 from the left, is 0. As x approaches 0 from the right, it's 0. This one does exist. So we had two functions whose limit did not exist at 0. When I added them together, created a new function where the limit does exist at 0. So you need to be aware of that. So just because one of them does not exist does not mean automatically that the limit involving some function created by those doesn't exist. It just means you cannot use these properties to evaluate it. So we have to have alternate methods of doing so. Okay, I have another example down here we're going to take a look at. Help us using some properties. Let's see right here. So I laid it all out for you. Here's some things we're given. We're given that f of 2 is 3, g of 2 is -6, h of 2 is -3. The limit of the function f as x approaches 2 will be 4. The limit of g of x as x approaches 2 is -6. And the limit of h of x as x approaches 2 is 2. So given that information, what is this limit right here? Okay, so we can use this is where you could kind of use your properties to help you work this out. Okay, so what's going on here? Well, I have a times in here, so I can use the product rule. I have a sum here, a constant times the function here. So if I do that, I can look at this problem in this fashion. I can say, okay, this right here can be written as the limit as x approaches 2 of h of x. Okay, I'm just going to separate here with some parentheses, times, because of the times here, the limit, let me put another parenthesis here, of this one right here, and the sum. So this would be the limit as x approaches 2. I forgot my 5 here, because it's a constant, so I can put it in front. So it would be a 5 times the limit of f of x plus the limit as x approaches 2 of g of x. So there's that. And so then I can come over here and plug in the numbers that I know. What is the limit as x approaches 2 of h of x? 2. This is going to be, over here, it'd be this, and then it's going to be a 5 times this limit, which is 4. And then it's going to be plus this limit, which is -6. And then we work all this out, and you see this is going to be what, 20 minus 6, and then times it by 2, and you're going to get 28. So this limit right here is 28, based off of these values up here. Now, here's just a few examples that we're going to be doing and looking at, and we are going to come together and do more problems in class to help us solidify our understanding. So that ends part 1 video.